For centuries, people have looked to the stars to find answers to our deepest questions. But with each discovery, more mysteries are revealed. From the mysterious physics of black holes to alien visitors from the past, our universe is full of riddles that challenge our understanding of reality. Join us as we delve into the world's most fascinating mysteries. When matter, or energy falls into a black hole, we are faced with one of the biggest mysteries of modern physics. Imagine a particle that contains detailed information about its properties, such as its position, velocity, and unique properties. When a particle crosses a threshold, a boundary beyond which nothing can hide, that information disappears from the world we see. This phenomenon raises fundamental questions, as the laws of quantum mechanics dictate that information should never be lost. The nature of information destruction in black holes challenges our understanding of the fundamental nature of reality and the relationship between energy and quantum mechanics. This contradiction between quantum mechanics and the general theory of relativity is known as a statement of paradox. Stephen Hawking once suggested that information trapped in a black hole could be lost forever, but this idea contradicts the principle of quantum determinism, which states that the past and future state of a system can always be determined from its present state. Recent theories, including developments in string theory and the holographic principle, suggest that information can be stored in some way. One idea is that information is encoded at the event horizon itself, like a hologram, retaining details but not losing them inside the black hole. Another interesting concept is Hawking's concept of radiation, according to which black holes can emit radiation over time and eventually vaporize. Some scientists speculate that information may slowly seep through this radiation, albeit in a highly encrypted form. This complex interplay between quantum mechanics and general relativity remains one of the deepest mysteries of physics, prompting ongoing research and debate. Each step forward in understanding promises to shed light not only on the nature of black holes, but also on the basic workings of the universe. Supermassive black holes, which range in mass from millions to billions of times the mass of our Sun, are mysterious giants that reside at the centers of most galaxies. Their formation is still the subject of active research, combining several fascinating theories into a compelling narrative. The prevailing hypothesis is that these supermassive black holes originated as small black holes of intermediate mass. Depending on the parameters of the planets, they grow and absorb gas, dust, and even entire stars from their surroundings. This process of accretion and merger of black holes will continue to grow in size. Imagine an insatiable alien that devours everything under its spell. According to another theory, the embryos of supermassive black holes may have formed very early in the history of the universe, a few 100 million years after the Big Bang. Under these primitive conditions, massive gas clouds would fall directly into the supermassive black holes, breaking a cycle of star-sized black hole formation. This process, called direct collapse, explains the appearance of supermassive black holes in the early years. Galactic mergers also play an important role in the growth of these black holes. When two galaxies collide, their central black holes can merge to form a large black hole. When galaxies merge, large amounts of gas often move toward the center, causing a black hole to grow rapidly. For billions of years, these Goliaths of gravity have been shaping galaxies around them, influencing star formation and the dynamics of galactic nuclei. Understanding their formation not only reveals the mysteries of these cosmic titans, but also provides crucial insights into the evolution and structure of the universe. Hawking radiation, proposed by physicist Stephen Hawking in the 1970s, is a groundbreaking concept that combines the principles of quantum mechanics and general relativity theory to explain a previously unimaginable phenomenon. Black holes can emit radiation and gradually evaporate over a very long time. Near the black hole's event horizon, the boundary beyond which nothing can escape, quantum mechanical effects come into play. According to quantum theory, particle-antiparticle pairs are constantly being created and destroyed in space, even in the vacuum surrounding a black hole. Sometimes, These pairs are created right on the event horizon. Due to strong gravitational effects, one of these particles is trapped in the black hole and the other flies off into space. The escaping particle takes the energy of the black hole with it, greatly reducing its mass. These escaping particles are what we know as Hawking radiation. Over a very long period of time, the black hole loses mass and energy as it continues to emit Hawking radiation, shrinking in size. This process is known as black hole evaporation. The actual evaporation of a black hole is a slow process. For most black holes, especially supermassive black holes, this happens over a period of time longer than a cosmic year. However, for small black holes, the mass loss increases as the size decreases, leading to a final burst of radiation before disappearing completely. Hawking radiation not only provides a mechanism for black hole evaporation, but also bridges the gap between quantum mechanics and Einstein's general theory of relativity. It serves as a step toward understanding the deeper connections between the laws governing the smallest particles and the largest structures in the cosmos. The idea of harnessing the energy of rotating black holes is not just a figment of science fiction, but is based on fascinating theoretical physics. Spinning black holes, also known as Kerr black holes, have enormous amounts of angular momentum and gravitational energy. This apparent paradox involving the use of the enormous black hole force was first proposed by physicist Roger Penrose in the form of the Penrose process. The Penrose process involves a particle that enters the ergosphere, a region outside the event horizon of a spinning black hole where space-time moves at zero velocity. In the ergosphere, a particle can be split into two parts. Some of it enters the black hole and some of it flies out, having gained more energy than the original particle. In this case, the process removes some of the rotational energy of the black hole. Another interesting concept is the Blandford-Znajek process. This theory suggests that the magnetic fields surrounding the black hole may interact with its rotation, sending energy outward in the form of powerful electromagnetic radiation. The jets of high-energy particles that are often observed from regions around supermassive black holes in the centers of galaxies may be a sign that such energy extraction mechanisms are at work. These theoretical methods offer tantalizing possibilities, but come with enormous practical difficulties. The extreme conditions and enormous scale make actual energy extraction a difficult, if not impossible, engineering feat nevertheless. The study of these processes enriches our understanding of black hole physics and the incredible forces operating beyond our scientific understanding. Although we are still a long way from building black hole power plants, these ideas push the boundaries of what is possible, encouraging us to explore more deeply into the universe's most mysterious entities. Regardless of whether we will ever be able to harness this energy directly, the principles underlying these processes continue to provide profound insights into the nature of space-time and gravity. If you enter a black hole, your sensations will be strongly influenced by its size and mass. For a black hole of stellar mass, typically several times the mass of our Sun, the journey would be unusually violent and short. However, falling into a supermassive black hole, millions or billions of times the mass of the Sun, can provide a longer but no less unsettling journey. As we approach the event horizon, the point of no return, the effects of gravity become extreme. In the case of a stellar mass black hole, tidal forces, extreme differences in gravitational pull, will stretch and compress your body in a process fancifully called spaghettification. You would be stretched in the direction of the black hole's attraction and compressed in other directions, which would quickly lead to your demise before you even reach the event horizon. In contrast, if you were to fall into a supermassive black hole, the tidal forces at the event horizon would be less intense due to the greater distance to the singularity at its core. Theoretically, you can pass the event horizon without immediate catastrophic spaghettification. As you fall deeper and deeper into the black hole, the view of the outer universe will shrink to a small, bright dot directly overhead, which will slowly fade as you approach the singularity, where gravity will crush all matter to infinity. Once outside the event horizon, the laws of physics as we understand them break down. Theories suggest that time and space become interchangeable, leading to speculation about what might happen. Some suggest that you could encounter a singularity, where matter would be compressed to an infinitely dense point, and that would be the end of your journey. Others suggest the possibility of reaching a region where space-time can connect to another part of the universe via hypothetical constructs called wormholes or Einstein-Rosen bridges. Whether the final moments involve meeting the singularity or traveling through exotic cosmic paths, falling into a black hole remains a mysterious and dangerous final journey, an exploration at the very edge of our scientific understanding. The discovery of exoplanets, planets orbiting stars outside our solar system, involves several inventive methods, each utilizing different aspects of astronomy to uncover these hidden worlds. One of the most successful and widely used methods is the transit method. When an exoplanet passes right between the parent star and us, this causes a slight periodic attenuation of the star's light. By carefully tracking and measuring these brightness variations, astronomers can determine the presence of an exoplanet, its size, and even some clues about its atmosphere. Another powerful method is the radial velocity method, or Doppler method. This approach relies on detecting small changes in the position of the star, which is attracted by the gravitational pull of the planet. As the planet rotates, it causes the star to move slightly toward and away from us. This movement changes the star's spectrum, shifting to light blue as it moves toward us and to red as it moves away from us. By studying these energy changes, scientists will be able to determine the exoplanet's mass and orbital period. The direct imaging method, although complex, involves taking actual images of exoplanets by blocking out the overwhelming glow of their parent stars. Using modern instruments and techniques, such as coronagraphs or stargazers, astronomers can pick out the faint light reflected or emitted by the exoplanet. This method is particularly useful for studying large exoplanets that are relatively far from their stars, in regions where the contrast between the light of the planet and the star is less dazzling. Another intriguing approach is gravitational microlensing, which exploits the warping of space-time caused by a massive object, such as a star or planet, passing in front of a more distant star. The gravity of the intermediate object acts like a lens, magnifying the light of the background star in a specific pattern. If the exoplanet is part of an interstellar system, its presence can be determined by characterizing its light curve. These methods, often used in combination, have discovered thousands of exoplanets and painted a diverse and fascinating picture of planetary systems beyond our own. As each object is discovered, our understanding of the universe expands, showing how powerful universes can be, capable of supporting life in conditions very different from those we know.